Okay, so here's the next of our short conversations. This time we're going to talk about some of the measurements we make in the ocean and how we use them to observe. You remember that the ocean is vast and diverse, which means that we have a lot of different scales of both length along this axis and time along this axis to explain. All of these sloping lines are named phenomena within the ocean. And here I've added the box that shows you about what a typical model would resolve of this domain. So there are things that are both slower and smaller than a model would be able to capture. So when we think about this, we start to wonder, if the ocean is so vast and so diverse, how do we decide what we're going to measure? Practical things like how long a scientist lives have a very large impact on this, because somebody will make their life's work to measure one particular part of the ocean for their whole life. The duration of an experiment in terms of what we can afford or just how long we can bear to be at sea has a lot to do with the scale of experiments. And linkages of the time and spatial scales that have the most practical use for things like shipping or fishing have a lot to say about what gets measured. Reproducibility is an important aspect of what we measure. You want to go out to a place that you can find over and over again, and maybe you look at the same season, or maybe you look at a complete seasonal cycle on the hopes that you have captured something typical about that place. Aliasing is a technical term that we're going to talk about in a minute. It has to do with different measuring things that are either at lower or higher frequency than the things that you actually have within the data you've collected. Sometimes you might go out to the most energetic part of the world. So you might go to the Southern Ocean to observe the Atlantic Circumpolar Current, or you might go to the Pacific to observe the Kuroshio. Often you're limited by the instruments you have. So sometimes you got a hammer and you go out into the ocean looking for nails. And finally, practical constraints, like if you happen to be borrowing ship time, if you know that there's a ship that's going back and forth, there's a ship called the Oleander that goes back and forth between New York and Bermuda, and it does that trip a couple times a week. And it's had an oceanographic instrument on it for decades, and they have transects all back and forth, back and forth, back and forth, back and forth. That's really a practical constraint, but as that record gets longer and longer, obviously it becomes more and more valuable. So, one thing we're going to talk about the averages or the mean, or the expectation value, but when we think about this vast range of scales, one of the questions you might have is, well, which scale is the mean at? And that actually is, when we talk about the climatology of the ocean or the mean circulation, it's not clear that that has a real answer, because there's variability on every time scale from seconds to millennia. So here is a map, here is a power spectrum. So a power spectrum is a way of taking a Fourier, that is frequency by frequency decomposition of a time record. This time record happens to be the Pacific sea surface temperature record. And so there are a bunch of different paleoproxy estimates that are used to fill in this range of time scales. And this is in frequency. Here's 1 year. Here's 1 cycle per 10 years, 1 cycle per 100, per 1,000, per 10,000, per 100,000. And you can see this slope, not only does it has big spikes like at the annual cycle and here at the tides, but it also has more stuff up here at these very long time scales. So the way you read a power spectrum is that each nugget of the power spectrum, each little small interval, if you integrated, that is, took the area underneath that curve, that would be the amount of power, that is, in this case, how much of the temperature variability is captured by just those frequencies in that small band. So if we integrate over this whole power spectrum, we would get the full variance over the whole time series. But if we just picked out this part, we get just the annual cycle, or here we get just the decadal cycle. Here's El Nino in here. So you can kind of understand how that works. We're not... this is just the temporal averaging of a particular location, but what about the spatial variability? How many observations did this require to make this? Are these actually sampling all at the same time, what we call synoptic scales? Or is this actually a meaningful way to process this data? What are the time scales associated with different spatial scales? You know, like how big is this temporal variability? How big is this temporal variability? Are there other physical scales to consider? The annual cycle is a good example. That's a physical time scale because it's how long it takes the Earth to go around the sun. And these tidal ones are also how long the Earth takes to go around the Moon and the Earth are in revolution and orbit about one another. So that's the kind of thing that you can think about. We can get started trying to think about. So when you say what's the mean, well, the mean is taking some amount of this and averaging over it, but there's probably that mean, whatever you chose, would vary if you had had a longer record. So our focus is going to follow traditional oceanography, where the time interval is typically greater than 1/2 of a pendulum day, the Foucault pendulum. That's the inertial period. And we're going to learn what an inertial oscillation is, and then that will make sense. But that means that we're paying attention to things where the rotation of the Earth is important. We're going to think about scales that are less than basin scale, that is the motions of the oceans. And mostly, we're going to think about things that are greater than the eddy scale, which is going to give us the ability to reduce the nonlinearity in the dynamics. And I always like to joke that this is like the Fiddler on the Roof. Tradition, tradition. That's really the reason why we call this oceanography. There are lots of interesting other things to do on different length and time scales than we choose. So we go back to those observational cruises, those campaigns, and now we think, well, yeah, they took a measurement, but all of that was probably just a snapshot. You know, maybe it took a few years to do this. But what about if they'd gone back a decade later where they've got a different answer? These are maps of temperature and salinity. Another really interesting way to present the data is a so-called TS map, where we put salinity on one axis, temperature on the other, and then we contour the density of the observations. So here happens to be the mean, and this red to blue scale is giving the number of observations within a given bin on this axis. So these are the most likely temperature and salinities. And hey, look, they're really cold, 4 degrees Celsius, pretty salty, 35 parts per thousand salinity. But there's also much warmer water, much fresher water. And then interesting anomalies like this, where this is really salty in a particular temperature range. And so we will come to associate the different spikes and deviations on this kind of a figure as an indication of a particular type of water, a water mass that's formed in a particular place at a particular time. It gives it a characteristic temperature and salinity. Okay, so most of the ocean is similar, but differences are key. This is showing a histogram of temperature and salinity volumes, showing a narrow distribution around the most likely, around the peak. The standard deviation here's the mean, and in this particular case, where this little subsample, the temperature is offset to be quite a bit colder than the mean. Oh, sorry, never mind. This is the mean of this distribution because it has a long tail to one side. So the most likely value and the mean are not the same, which is because this is not a normal distribution. In this case, the salinity looks kind of normal. So one of the things you could think about for your first paper is really Could you tell two different locations apart in terms of their salinity or their temperature or both together? If you plotted the histograms of observations next to each other, would they be distinct peaks? This is some helpful data for you. This is just the volume of all the world's oceans based on a particular mapping system called eTopo. These are some helpful numbers to have. You can come back to this later. And as we talked about, this is another way of thinking about those water masses. So here they are formed at the surface, like we talked about last time, moving downward. And now when you look at the potential temperature in the upper panel and salinity in the lower panel, you see that this North Atlantic deepwater has a really characteristic salinity, and it's probably a little warmer than normal. Go back here. It's like this kind of a feature. Extra salty, extra warm. Okay? So that's the kind of thing you can do going between the TS diagram and these kind of maps and contours. And remember, we said that the deepest water can be quite old, so it takes a long time after the water's formed to get down deep. All right. So now let's jump to the question of what do we mean by mean. Let's think about a little bit about what a steady state is. If the concentration of a substance is assumed to be constant with time, then the rate of input of that substance is balanced by its output. It's like money in the bank. If the balance of your bank account is constant, the rate of spending and the rate of deposits have to be equal. Same thing here with a substance. So you can apply this to any of the elements in the table of elements, or to a quantity of water, to something that's conserved like heat energy, to populations of fish, etc. The average amount of time that a given atom of a given element stay in solution is called the residence time. And the residence time is the total amount that's present dissolved divided by either the input or the output rate. You can use either because, as we just said, if the concentration is relatively constant, then the input is equal to the output. So if you take the concentration divided by the input or the output rate, that gives you a time scale. So here are the residence times of a bunch of constituents. So sodium chloride is salt, right? Those two together, they stay in suspension basically forever. So very, very long residence times. Whereas iron actually doesn't dissolve well and tends to precipitate out of seawater. So it has a relatively short residence time. In fact, you can plot profiles of all of the elements in the periodic table. And if I could read this, I would be able to tell you which one was which. So here's sodium. Sodium, as we said, is part of sodium chloride, and see how it's just pretty much constant. There's no variation. That's because it's in the water so long that it's totally mixed up. Everywhere in the water has been mixed and mixed and mixed and churned over that 1,500-year time scale, many times over before it gets to the residence time of sodium. So it's well mixed. Whereas something that precipitates out quickly, in here, they have very complicated structures because they are either have surface sources or deep sources, and then they're reflecting the time history, how far they are from the source. Or it might be biological processes. The biology is normally up here in the carbon-nitrogen area, but carbon and nitrogen are consumed by biology or emitted during the dissolving of nutrients, detritus, and so they have an interesting vertical structure. I should have said this is vertical structure with depth in each of these profiles. So one way to estimate the residence time is to look at the vertical structure of a particular constituent, trace element. Okay, another thing to measure about the ocean are looking at things from satellites. So we can measure the sea surface temperature. And this is done with electromagnetic radiation emitted or absorbed by the surface. Ocean color, which can be used to estimate chlorophyll, pollutants, blooms, sea ice. Sea surface salinity actually has a signature, enough of a signature that you can measure it from space. You also can measure gravity from space by putting two different satellites, one behind the other, and measuring distance between them very carefully. This is called the Gravity Recovery and Climate Experiment. We talked a little bit about this last time. And you can also do altimetry, which is where you bounce a radar or a laser off the surface. That gives you quantities like sea surface height, sea surface roughness, which indicates waves, and then waves are there because of the wind, so you can relate that to the winds. And you can actually do something called synthetic aperture radar, which is a fancy processing of this kind of radar signal, which gives you small scale roughness. Sometimes you can see things like biological slicks or wave crests and that kind of a phenomenon. These are the things you can see. They're all surface properties except for the gravity satellite. And here's one example that we talked about last time is the altimetry, where you bounce an altimeter off. You have the sea surface, it's going up and down. The geoid is somewhere different. The ocean topography is still another distance. We talked today about whether the difference between the geoid and the ocean topography has to do with potential energy. And the so as this spacecraft moves around and around the Earth's center of mass, it's measuring all these things by bouncing either a radar or a laser signal off. Tide gauges, just a float, it goes up and down with a record, tells you how high the sea surface is versus a reference. These are some of the oldest records taken of the oceans. Obviously, these are important for sea level rise, but also for waves and tides. And this is an example of what that Quikscat wind field looks like. This is measured by measuring the roughness of the surface from a satellite and then inferring the wind speed that has to go on. So here is the wind speed down here is measured in newtons per cubic meter, which is kind of a funny unit. But anyway, that's a measurement of the wind stress, I should say, rather than wind speed. And it's actually the wind stress curl, which is why it's per meters cubed. It's a derivative of the wind stress. But you can see all these little small scale features, which we didn't really know about until we had this satellite. So you put it all together, you get very complicated motions like this. This motion is actually recreated by me from the surface kinetic energy as inferred from an altimeter or a combination of altimeters called AVISO. You need to get other kinds of instruments to get into the deep. You can only see the surface from satellites. What are some of the deep instruments? CTD measures conductivity, temperature, and depth, or actually really measures pressure with a strain gauge. But you put those three together and that's the classic measurement of the ocean. Just like the reversing thermometer could measure those three properties, we now have an electronic kit. It's a small thing. It's only about the size of, your thumb that measures these three at the same time. We talked about the reversing thermometer. We talked a little bit about acoustic Doppler current profilers. That's the idea, is that you bounce sound off of moving particles in the water. It could also be lowered, ADCP, or it could be mounted on something like a buoy. There are lots of different bottles. Bring up some seawater, measure stuff in it. Lots of different nets, catching things. Deployment, you can do it while you're running, just dragging something at the surface. You can go up and down as you run, called a tow-yo. You can cast, which means like dropping it over, lowering it down to depth, bringing it back up. You can do a surface, even a continual surface measurement. Or you could do a release of something and then measure it at a later time and see how it's spreading out while you're not watching. A mooring is different from a float. It's a buoy at the top with an anchor at the bottom, or sometimes the buoy is subsurface. And there's typically an acoustic release somewhere so that you can reclaim all these instruments at the end and gather all the data. But if they have a surface signature, they may also be sending back satellite signals. This array of moorings around the tropical oceans around the world is serviced and is This is one of the key data sets for us if we're looking at El Nino or La Nina or other variability in the Indian or Atlantic Ocean and the tropics. Along the anchor line, you have lots and lots of other instruments. So you might have a current meter, you might have a thermometer, something's measuring the tension, acoustic beacons, ADCPs. There are even some robots that crawl up and down along the chain and measure things continuously. So lots and lots of measurement types. For those of you who have taken some fluids, really a mooring is an Eulerian instrument. It stays fixed at a place and gives you a time series, rather than a Lagrangian instrument, which is something that follows the fluid as it moves. One other example of moorings that we're definitely going to use is the rapid mooring array. There's also two new ones called the SAMOC and the OSNAP, which are monitoring the meridional overturning at a particular location. Rapid is at 26.5 north. And from that, you get a time series of things like the Gulf Stream, meridional overturning, Ekman currents, which we'll explain, and other currents. The ADCP has these multiple beams. We talked about that last time. You can also look for the bottom using sonar. And floats could be mounted with a CTD and a cell phone. And off they go, over and over, up and down, like that. Surface drifters, something like this, a Carthy drifter, this is a biodegradable plastic drifter. So you throw it in, and then it has a GPS inside, and it just tracks its movement for as long as you leave it out. It's good for tracking oil spills or other things like that. Some drifters have a longer, this is called the drogue, this little sail below that moves along with the water. Some of them might have a much bigger drogue that goes much deeper, and so it depends on what depth of current you're trying to measure. These are Lagrangian instruments. They travel to some extent with at least the surface flow. They move around. You can set them to stay at a particular pressure or at a particular density. They can be kept at a particular depth or density, and they often are fitted with CTDs that gives you a profile as they go up and down, or a time series at that particular depth or pressure level. Before there was GPS, they used to be acoustically tracked. And first they put a sound source on the drifters and a microphone all around to hear it. And then they realized, so that was called a SOFAR float. And then they realized that it was better to do it the other way around and put a microphone on the float and the sound sources all around. And that's called a RAFOS, which is just the inverse of that. These kind of techniques are really good in the deep ocean, but they require sensitivity to whether you might be disturbing marine mammals or other things like that with this kind of sound sources. These are typically relatively weak sound sources, so they're limited in range. When you have floats, you stop having these big gaps of no measurements, and you start having more uniform measurements all around the world. And that allows you to detect these kind of horizontal features that we talked about last time. Here's a nice example of a drifter release. This is from the Carthy experiment. So the red line is showing the ship that's going around, and as the ship drives around, it's releasing those drifters. And now you can watch the drifters tracking around, measuring some kind of big swirling eddy feature here. And the streaks are indicating their time, which indicates essentially their velocity. And then the last thing that I wanted to talk about is fine structure. We talked about this a little. This is a very high accuracy CTD, or something like a CTD, called a microstructure probe, and it is able to calculate or detect very, very fine variations in salinity and temperature. So fine that the smallest turbulent scales in the ocean can be inferred how strong they are from that. So you take one of these instruments and you drop it, and it profiles, and we find upon that turbulence varies a lot based on the roughness of the seafloor below, but also things like how strong the currents are and how strong the tides are above it. And that's related to these intervals of mixing and unmixing that are discussed in Wunsch. And the last thing that I want to talk about was paleoclimate records. So a lot of you have taken the paleoceanography class from Tim, or the Quaternary paleoclimate class from Jim, or other paleoclimate classes in our department. Anyway, the key tools are things like ice cores and sediment cores, but also land-based things like tree rings, pollen, gives us a sense of the past climate and geologic record. For things that are older than we have been, or slower than for how long we have been making records of temperature and salinity and things, so things basically over 100 years, these are the only observations we have. And that's where this time series is so powerful that comes into play from Hoybers and Curry. There are lots of other platforms, crazy things that you can read about, and you can find out about them in Wunsch. That's not too important for where we want to go, except you might find something fun to examine. You might want to look, for example, at marine mammal-based observations. So we put all this stuff together, all these different satellites, all these different in situ measurements, we stick it into a model, and we get something that looks like this. This is a model, a data assimilating model that includes all of those kind of data. You can see the sea ice coming and going, you can see all the eddies, all this sort of stuff. All right, that's all I wanted to talk about for today. So the key concept is there are lots of different instruments. For this first paper, you want to pick one and tell a good story with it.